Hello girls, how are you? Let's continue our lesson, the last part of circular motion. Today we want to talk about dynamics in circular motion. Before I start explaining, I want from you to watch this video. Now we are going to watch it together. After that, I will start explaining the lesson. Let's start.
We had to come up with a good excuse to visit Wild Adventures. This place is full of reasons to learn about physics, starting with going in a circle. What if I'm moving in a circle on this ride at a constant speed? How am I accelerating? Anytime an object is traveling in a circular path, it is accelerating because its direction is constantly changing. Now remember, velocity is a vector. It has magnitude and direction. If either changes, velocity changes. And acceleration is defined as a change in velocity. Let me show you an example. You ever wonder why you can swing a bucket of water like this and the water doesn't spill out? It's because of centripetal force. It's a word that means center seeking, and it's written F sub c. Centripetal force is any force that makes an object move in a circle. There's more than one kind of centripetal force: friction, tension, the normal force, or gravity. And any of these can act as centripetal forces if they cause the object to move in a circle. Here's another way to say it. Centripetal force is the net force acting on objects that keep them moving in a circle. When I swing the bucket, there are two questions. Which force makes the bucket move in a circle, and what keeps the water in the bucket? There's a fine balance here in keeping the water in the bucket. So what forces are acting on the water in the bucket? Well, let's draw a free body diagram of the bucket first when it's at the top of the swing. The force of gravity, F sub g, acts down. Tension, F sub t, acts down on the bucket as well. The force of gravity will act down regardless, but the tension force will always act toward the center of the circle. In this example, the tension force and the force of gravity create the net force, and together they make the bucket seek the center of the circle through the centripetal force. In a free body diagram, you don't write centripetal force per se. You write in the specific force or forces causing the centripetal motion, in this case, gravity and tension. So what forces make up the centripetal force when the bucket is at the bottom of the loop? You can see that the tension force still acts towards the center, and gravity continues to act down toward the earth. So what keeps the water in the bucket? It's the normal force of the bucket on the water's inertia. Tension keeps the bucket moving in a circle. The water within the bucket experiences the normal force from the bottom. This force keeps the water moving in a circle. If we were in the middle of space and there was no gravity, the water would still stay in the bucket as it was swinging in a circle, thanks to the normal force. And what force keeps the bucket going in a circle? Well, that's easy. It's the tension of the rope. Okay, what if there's no rope? For example, what force keeps a satellite orbiting the Earth? It's gravity that pulls the satellite toward Earth and keeps it in orbit, so the centripetal force is Earth's gravity. It's the tether that keeps the satellite orbiting around a central point instead of flying off into space. But keep in mind, it has to be going at a certain velocity to stay in orbit. If the satellite slows, it will give way to Earth's gravity and fall to Earth. So let's take a few circles around this track. The only difference between this and the bucket of water swinging in circles, the bucket of water swings in vertical circles. The circle we're traveling in here is horizontal. But the good news is the same principles apply. So based on that, what forces keep this cart moving around the circular track? Frictional force is at work helping the tires grip the track and keeping the cart in a circular path. Vertical forces on the cart cancel out. The cart is center seeking, only in the horizontal direction.
Okay, great girls. This video it is an amazing video, and it will help you a lot to understand the concept of dynamics in circular motion. So I will start explaining after you watch the video. Now, objects in circular motion are being accelerated toward the center of a circular path. We talked about centripetal acceleration, right? This implies that the net force is also directed toward the center of the circle. You remember Newton's second law? Force equals mass times acceleration. So, whenever there is acceleration, it means that there is a force. In uniform circular motion, the net force is known as centripetal force. We write it F sub c. So girls, centripetal force, it is not a name of a force. It is the net force that in all forces that are acting on the object at any moment in a circle or a circular motion. We call these forces, when we add them, centripetal force. So net force is the centripetal force. So we don't have a particular force the same as friction or tension or normal or gravity. We call it centripetal. No, centripetal is the name of all forces acting on the object. Okay, I hope that this point is clear. Let's look here. Here's the formula for centripetal force. You remember Newton's second law, force equals mass times acceleration. The same formula. Here instead of force, we wrote F sub c, centripetal force, equals m mass times v square over r. What is this formula? Centripetal acceleration. You remember centripetal acceleration, v square over r. And you remember we said before, in a circular motion, centripetal acceleration always directed toward the center and centripetal force always directed toward the center. So both of them are going the same direction toward the center of the circle. Okay, let's study some cases about circular motion that he explained in the video. The first example he talked about, it was the bucket of water, vertical circular motion of bucket and water. In this case, what kind of force provides the centripetal force to the bucket at the highest position? At the highest point here, what forces we have? We have two forces. Tension from the rope or the string and force of gravity. It is, we have always force of gravity and also toward down. So what is net force equal? It is the sum of tension and force of gravity, which is mass times free fall acceleration. So here, if I ask you what kind of force provides the centripetal force, the answer is tension plus force of gravity. Okay? At the bottom, when the bucket is here, at the bottom, what do we have? Tension is toward where? The center of the circle, because here is the rope, it will be here. Here's the bucket, so the rope will be here, the string. So the tension is directed toward the center of the circle, toward up. And the force of the gravity for sure toward down. All the time, force of gravity toward down. So in this case, the centripetal force, what it equals, not the sum of them. It is what? One of them is positive, one is negative. Tension is positive because it is directed toward the center of the circle. Because here in circular motion, any force acting toward the center, we assume that this force is positive. Any force away from the center, it is what? Negative. So here, that's why, now both of them are going toward down, okay? But we said that positive and positive. Why? Because they are directed toward the center. Here, the tension is positive, the force of gravity is negative. Why? Because this one toward the center, this one away from the center. I hope that this is clear. Girls, these cases are very important because in the questions later on when we start solving, I will not tell you the forces acting on the object. You have to know. I will just give you this question and you have to know by yourself the forces are going toward where. You have to know how to draw free body diagram of the bucket at the top and at the bucket at the bottom. The second case, vertical circular motion of a roller coaster. You know roller coasters? We have so many cases in roller coaster. We want to study two cases, at the bottom of a roller coaster, at the top. Now here in roller coasters, we don't have tension, we don't have a rope. What is the force that's acting on the car? Normal force. It's the force between the tires and the rail toward up, for example, or toward down. So here when the car is at the bottom of the loop, we have two forces acting on the car. Force of gravity toward down as usual. Normal force is toward up. Here is because here's the car. So the normal force from down toward up, pushing the car toward up. You remember normal force? Force between two objects in contact. Here, in this case, so here, centripetal force, what it equals? It equals normal force minus force of gravity. This one is positive because it's toward the center of the circle. This one is negative because it is away from the center of the circle. The second case, when the car is at the top of the loop. In this case, both forces are directed toward down. Why? Because normal force is from here toward down, right? Force of gravity always toward down. So the centripetal force here equals normal force plus force of gravity. This is the second case, and it is very important. The third case, we have it horizontal circular motion of a car. So if I have a car, now here in the first two examples, we are talking about vertical motion, and here also vertical motion. Cars, for sure, they are moving what horizontally, okay, in a circular path. So you have a road, this or a curve, and this circular path, and the car is moving in this road. So what is the force that causes the car to move in a circular motion? It is frictional force, always. Frictional force directed toward the center of the circle. Here's the circle. Friction force is the force that causes the object to move in a circular motion only. We don't have any other forces. So centripetal force here equals only force of friction. You remember the formula for force of friction? Mu times normal force. Now we have forces acting on the object vertically, but these forces, they have nothing to the horizontal motion, normal force and force of gravity. But the only force that causes circular motion here is force of friction. Here, gravity and normal. Here, gravity and tension. Okay? Look at the difference how. Good. After that here, after we talked about all the cases, let's see if we have any question, any dynamic question asking about circular motion, what we have to do step by step in all questions. Number one, you have to draw a force diagram or a free body diagram. Okay, if the motion is circular, any force vectors pointing toward the center, always positive. Remember this note. Those pointing away from the center are negative. The second thing, determine the type of motion to see what type of motion we have, vertical or horizontal. We have force of gravity, we have normal force, we have friction. What exactly do we have? Okay? Add all forces pointing toward the center of the circle and subtract all forces pointing away from the center. As we said, what you have to do. The last thing, substitute the equations. And centripetal force, we know the equation for it. mv square over r. You write it here under it. Here, for example, if I have force of gravity or tension force, tension, it's tension. We don't have a formula for it. If it's a force of gravity, it's mass times g. If there's a force of friction, mu times normal force, so on. Okay? These steps, you have to do them in each question. Let's see now the first example and how we are going to solve it. Horizontal circular motion. A car moving at 10 meters per second completes a turn with a radius of 20. So the radius is given, tangential velocity is given. Determine the minimum coefficient of friction, mu, between the tires and the road that will allow the car to complete the turn without skidding. Okay, girls, here we are talking about what type of force? Horizontal. What is it? Car. So what is the centripetal force here? What? You have to know direct force of friction. First step, you have to draw a free body diagram. This one, exactly the same as this one. To show me that force of friction toward the center, these two forces up and down. Okay? Then, this is number one. Number two, the second step, you have to write the formula. Centripetal force, what it equals? Force of friction only. Then you substitute for each Here, for the formula for each one, centripetal force, mv squared over r, friction force, yes, it has a formula, mu times n. And we know that normal force equals what? Before we took it, equals force of gravity, which equals to mass times g. Okay, so instead of nu, I want you to write m times g. That's what we are going to do. We want to find the mu, so I will leave it in one side alone, and I will write the other variables on the other side. Then I start to substitute the numbers, magnitudes. At the end, you will find the answer 0.5 without any unit because the coefficient of friction has no unit. Okay? I hope that this question is clear. The second example. Now here, vertical circular motion. A 2 kilogram mass is attached to the end of a 1 meter long string. This is the radius. 2 kilogram, this is the mass. When the apparatus is swung in a vertical circle, the mass reaches a speed of 10 meters per second at the bottom of the swing. At the bottom of the swing, tangential speed equals 10 meters per second at the bottom. Determine the tension in the string at the bottom of the string. At the bottom, they wanted to find the tension. Now, what do we have here? They said string. So what are, and vertical motion? String. So draw a free body diagram. At the bottom of the swing, you remember what we said before? We have two forces acting on the object. Tension toward the center, force of gravity toward down. So we write the formula, centripetal force equals tension minus force of gravity. This one positive, this one negative. Then I want to find tension, put it alone, then start to write the formula for each one. Tension has no formula, leave it as it is. Centripetal force mv squared over r, fg it's m times g. We substitute, you find the answer direct, 220 Newton. Clear? The second part, determine the minimum speed at the top of the loop that allows the mass to make one complete cycle. Girls, this part is very, very important. I know that some girls will ask me, they say, teacher, you said that in circular motion, the speed is all the time constant, doesn't it change? That's true. It's correct. But they're asking, what is the minimum speed? And for example, not all the time you are going to swing the mass with the same speed. Okay, you can change your speed, sometimes faster, sometimes slower, but there is a minimum speed. If your speed is less than this minimum speed, the object will not move in a circle, and you will see that the mass at the top, if you are decreasing your speed and you are swinging the object, you will see that at the top the string will, or the object will fall, will not move in a circular motion. I want you to find this speed. How to find it? Focus to understand. At the top of the loop, we have two forces acting on the object toward down, tension and force of gravity. So, centripetal force equals tension and force of gravity. To get the minimum speed, we have to make one of these zero. To get the minimum speed, we have to make one of these zero. Because this is the minimum magnitude, we can get it, okay? Now, force of gravity, we can't at all make it zero. We don't have a case that force of gravity is zero on Earth. So not the force of gravity. We can make tension zero. We assume that tension zero. That we assume that here tension is zero. So we will see what is the minimum speed that I can't swing the object less than this speed. We assume tension zero. We substitute in the formula normally, mv squared over r, 0 plus mg. Then you find the minimum speed. Okay, this is the minimum speed. So girls, please understand this part of the question. Not only for this case. Now later on, in other questions about roller coasters, you are going to see the same case, okay? The same case how? If you have circular motion, they will ask you find the minimum speed at the top of the loop that allows this car to stay on its tail. It will not fall. So what do? Here we don't have tension. What do we have? Centripetal force equals normal plus force of gravity. In this case, you are going to assume that the normal, you are going to write normal equals zero. Okay? Always you have to do this. Always you have to do this when they ask you for the minimum speed at the top of the loop. Girls, alone, after you watch this video, direct please solve these two questions, try to understand them, solve them by yourself, then solve these questions. You have them on the PowerPoint and you have them also on your books at the end of this chapter. Okay, so today we finished our chapter. Tomorrow we are going to solve these questions and extra questions about circular motion. Thank you, girls.